Hey guys, Mr. Newman here, and today we're going to work on 4.7 optimization notes. There is a bunch of steps here that I'm really going to kind of blow through, and I just want to get to doing the examples, because once you see the examples, all these steps make sense. Like constraint equation, objective function, like what is this? Until you see a real example, it don't make a lot of sense. I do want to point out the first step we have is draw a picture, if there's not one already, and that's tremendously helpful. And some of the other stuff, you want to make sure at the end to answer the question, right? So I'll write or type a complete sentence to answer the question, yeah, just make sure you do that each time because that is 1 point for sure on these open-ended problems. So let's come on down here and I'll kind of point to the steps, but for the most part we're going to work through these. So we need to enclose, one comment before we get started. Hopefully we talked about this a little bit, but we're doing optimization notes, and the idea is these are actually problems you've done before, but now we can do them without a calculator and using derivatives, okay? So optimizations being a maximum or minimum if there's a situation such as using the most, finding the most area, or using the least material or the least cost or anything like that. That's we can find that because, remember, maximums and minimums are where the derivative is equal to 0. Those are our critical points. And so the idea is we find a critical point, okay, find the critical numbers, and then we're going to use our number line to make sure that the critical number we found is a maximum or minimum, depending on what we need. And then we're going to answer the question, okay? So that's the basic idea, so let's get started. First of all, you do want to draw a picture here. So we need to enclose a rectangular field with fence. We have 500 feet of fencing, and a building is on one side of the field, so we don't need any fencing on that side. So let's draw the building here. So here's the building. And then we've got our fence. So if it's rectangular, I'm picturing the fence on 3 sides, something like this, right? And I like to use W and L for length and width. So you can see most of these problems have 2 equations you set up. A constraint equation, one where you have something that equals a number, and an objective function. That's one that you're trying to maximize or minimize, okay? It tells us we have 500 feet of fencing material. That's perimeter, right? So we know that we can set up this equation, 500, let me use black for this. I'm going to write this down here actually. 500 is equal to the perimeter, so 2L plus W. I'm just adding up all the sides, right? That's perimeter. Determine the number of dimensions that will enclose the largest area. So we know our other equation is going to be something to do with area. Well, area area of a rectangle is just length times width. So there's our 2 equations. You go, what do we do with this? Well, what we can do is we can solve for one of the equations up here. Solve for one of the variables up here, plug it back into one of those 2, and then we take the derivative, and we're going to set the derivative equal to 0, because that's where there's a critical number, and that's where there'll be a maximum or minimum. I'm looking here, it looks, and you want to look and be thinking about what is the easiest variable to solve for, and here it's a little bit easier to solve for W, just because then you don't have to divide after you subtract. So let's just subtract 2L from both sides, so we get W equals 500 minus 2L. Then we're going to take this and put that back in for W because it's equal, so we have area equals length times 500 minus 2L. And notice we now have our thing we want to maximize, or minimize, in this case is maximize, right? Area, and we only have one variable on the other side. So we can take the derivative. I am going to simplify it though first before we take the derivative, because it's a little bit easier to take the derivative when you don't have to deal with product rule. So we get 500L minus 2L squared. So let's take the derivative. We got, and I like to use A prime, it's just a little bit simpler. 500 minus 4L. And so this right here, if we set this equal to 0, that's what gives us our critical number. So let's do that, and we can subtract 4L from both sides and then divide both sides by 4. So we get L equals 500 over 4, or 125. At this point, we want to set up a number line. So here we go, here's our number line. And this is a number line for the derivative. Okay, so I want to mark that to remind myself that's A prime. All right, I'm checking to see whether A prime is positive or negative, because that tells us whether the function is increasing or decreasing. And 125 is the length that is going to be our cutoff, right? And so let's see, if we plug in a number smaller than 125, remember we're plugging it into the derivative equation, so I'm just going to look right here. Plug in a number smaller than 125, you like say plug in 0, 500 minus 0 is positive, so we're going to be positive on this side. And you can look here and see this is a factor that has a multiplicity of 1, so it's going to be negative. You can also plug in a number bigger than 125. You're going to see like you plug in 1,000, 500 minus 4,000 is going to be negative. So if you need the graphical representation, it's positive and then it's negative. That means we have a maximum here, which is good because we wanted the largest area. Excuse me. However, it says determine the dimensions, right? Determine the dimensions of the field. So we have length, we also need to find width. I come back here and I find this is the easiest equation if I have length and need width. So I'm just going to put W equals 500 minus 2L. Oops, sorry, I didn't just write a little maximum there. That's hopefully you see that's a maximum, so that's largest, okay? We know that length is going to be 125, so 500 minus, that's 250, means that the width is 250. So I want to write or type something such as this. The dimensions of the largest area will be 125 by 250. And let's include units because you always want to do that. So 125 feet by 50 feet. We answered the question. We're good. Let's go on to the next one. Hopefully you saw that we really followed all these steps. The constraint equation and the objective function, those are these two equations here, the 500 equals and the area equals. We solved for the easiest variable. We substituted in. We simplified it, right? We did that so that taking the derivative was a little easier. And we found the critical numbers. And we did a number line for the derivative. We found the max min and we answered the question. Okay? So let's do this for another one. We want to construct a box with a square base. And we only have 10 square meters of material. Now I'm going to mark this right here. This, you see the meters squared, you should see that and go, ah, that is surface area because it's squared, right? That's going to be area. So that's not telling us the volume, that's the surface area of material. Let's draw a picture of this box. So it's a square box. That means on the base we have a square. Now I'm tempted to draw a cube, but I'm going to not draw a cube just so that you want to avoid drawing a cube unless you know it's a cube, because I'm trying to draw and talk at the same time, because you want to, if there is another variable you need to assign, you need to make sure you assign that, okay? So we'll use W here for width, and if it's a square base, then they're both width, so we'll use W and W, but the height is going to be something different, okay? That's why they might turn out being the same, but same number, but it's a different variable because it didn't say a cube, it says a box with a square base, okay? So let's see here, assuming all the materials used in the construction process determine the maximum volume. So we got maximum volume. So our two equations, one's going to be 10 equals the surface area, the other one's going to be the volume. The volume equation is easy because it's length times width times height, which in this case is W squared times height, right? However, the surface area is a little trickier. We're going to need to add up all the sides. So we have the base is W squared, and then the lid or the top is also W squared, so that's 2W squared. Then we're also going to add each of these sides. There are 4 of those, right? So 4 times, let's see, it's width times height, so W times H. And so that accounts for all 6 sides, 2, 1 on top and bottom, and then the 4 around the side. So let's now solve, and it might be a little tricky thinking, okay, what's the easiest thing to solve for, W or H? I'm going to say H is a little bit simpler. You run the risk, if you're solving for W, you run the risk of getting a square root. You also have to, when you plug it in, you have to square it. So I'm going to say let's solve for H. I think it'll be a little bit easier there. Of course, you're welcome to solve for whatever you want to. And the first thing I'm going to do is divide both sides by 2, just to make it a little bit simpler. We get 5 minus W, and then we divide both sides by 2W. Okay. There we go. So let's now take this and plug this in for h over here. And we're going to see some nice things happen. So w squared, 5 minus w squared over 2w. First of all, that w and w divide out. So we are left with, let's see here, this looks like 5 halves w minus 1 half w cubed. Yeah, so I divided both those by 2, went ahead and did that, and I'm realizing in my notes I had the wrong answer because I forgot this 4, I left off that 2 there. So we'll just continue with this. So that's our volume. So now we have something we can take the derivative of, so let's go ahead and derive it. So v prime is equal to 5 halves minus 3 halves w squared. Alright, so that's the derivative, and that needs to be equal to 0. So let's solve for this. So we get 3 halves w squared equals 5 halves. Multiply both sides by 2, and w squared is, let's just do, we'll do this. W squared equals 5 over 3. So w is square root both sides plus or minus root 5 over 3. But before we go much further, notice w is a width. So what does that minus mean? That means negative something. Width can't be negative. So actually it's important to always remember to do a plus or minus, but we really only need to think about the positive one because that's the only one that is going to be in the domain of our function, right? That's the only one that's going to matter. So good, we got the positive one, and we could have included the negative. We would have seen that it would have been eliminated in this next part, but it's better to eliminate as soon as you can. Oh good, I did get the right thing here. What did happen? That's yeah, so that didn't change the outcome after all. It's a little weird. Not has me concerned, but so square root of 5/3. If we have square root of 5/3, that's approximately 1.291. So I'm going to round that. Now notice I am going to, when we come back in and plug this in, you want to keep all the decimals. This is where you want to keep, if you have the store feature, STO, in your calculator, it saves it. I can also show you guys in Desmos real quick how to save that, but you really want to be using your calculator to practice with this. So you want to store this because you want to use as many of the decimals as possible to get an exact answer, right, when you get your final answer. But here we go. So this is v prime, remember. This is the derivative. And we're just checking to see if it's positive or negative. So if you plug in like 0 into this right here, that's going to be 0. It's going to be a positive number. So we have a positive. If you plug in a really big number, so say 100, this is going to be way larger, and it's going to be negative because of that negative there. So we're going to have a negative number there. So that means we're increasing and then decreasing. So this is a maximum, which is good because we want to find the maximum volume. All right. So now that we got that, that's a maximum. What was it asking for? Is determine the maximum volume the box can have. So we just have to calculate the volume. Well, here's an equation for volume. So if I just plug this in, I'll plug it into my calculator here. Let me show you guys real quick how to do this in Desmos. Okay, how to store things, I'll say, how to store them into Desmos. What you can do, you can have something like square root of 5 over 3, and you can say w equals, so it's stored, right? And it saves all of those as that variable. Then you come back here and you can plug in the original equation, 5 halves w minus 1 half w cubed, and look, it calculates it for you. Of course, you remember the store feature, you can do the same thing in your calculator. So our answer is going to be 2.15, 1 if I truncate or 2 if I round up. So, whoops, I just said it, I forgot. So the volume is 2.15, 1 if I truncate or a 2 if I round up, right? Now you do want to include units, so that's going to be meters. And so the maximum volume is, volume can be, would be meters cubed. Blah, 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 blah. All right. So volume is 2.151 or 2 meters cubed. And we're done with that one. Great, let's move on to the next one. We want to construct a box whose base length is 3 times the base width. So here a drawing is very important, so let me draw a picture of this. I'm going to draw, let's see here. Let's leave a little more space here. Base length is 3 times the base width. So I like trying to draw it to proportion just so I can kind of visualize and see what I'm trying to do here. So if this is the width, the length is going to be 3 times that width. The other thing I can do here is I can put down length is 3 times the width, so length is 3W. And in fact, later when I'm calculating stuff, I don't want to use L, I'm going to use the 3W. Now let's also put a height in this for this box. Let's see, let's not make it quite so tall. I don't really know how tall it's going to be. Woo. Make straight lines. I can make straight lines, I just can't make them go up and down. There we go. So we got our box here. There we go. Okay, that will help with explaining some of this. And we don't know the height, so we need to say H here, right? Now, this has a lot of information. The material used to build the top and bottom costs $10 per square foot, and the material used to build the sides is $6 per square foot. The box must have a volume of 50 cubic feet. Determine the dimensions that will minimize. Oh, and now we're going with the minimum. Minimize the cost to build the box. Well, first of all, we have volume. That's going to be 50. And I know volume is just length times width times height. But I'm not going to use length here. In fact, whenever possible, I'm just going to use 3W instead of length. Okay? That reduces the number of variables I have, so it helps me solve things a little faster. So we have the height times, let's just do this, 3W squared H, right? It's W times 3W times H. We got all of them, okay? The other one is the cost of the box. So we need to figure out the cost. And notice the cost is based on the surface area because it talks about $10 for the top and bottom and $6 for all the sides. So we need to do a little bit of thinking here. Let's do the $10 first. So it's $10 per square foot on the bottom and the top. And you can see here the bottom is going to be W times 3W, and the top is also going to be W times 3W. So I'm going to have W times 3W, that's 3W squared, and I need to multiply that by 2 because I have 1 on the bottom and 1 on the top. Okay? Then we're going to add to that 6 feet for the sides, and each side is a little different, so let's do the front first. The front and the back are actually the same. They're going to be width times height, okay? So 6 times width times height, and there's 2 of those, so we're going to multiply that by 2. Then we need to do the other side, so we have the right side and the left side. Hopefully you can visualize that shading in there. That's going to be height times 3W, so 3W times height, and here again we need to multiply that by 2 because there's a right and a left side. Phew. So all of that, let's simplify this a little bit first. I made the mistake of trying to substitute first. I think simplifying here would go a long way. So 3 times 2 is 660 W squared plus, we have 6 times 2 is 12, so that's 12, 6 times 2 times 3 is 36. So we're going to have 48 WH. Great. Okay. And so we have this. We just need to take the derivative of this, but first we should solve for one of these. Again, here, when trying to decide what to solve for, I see a W squared, so I don't want to get W by itself because that'll leave us with a square root. And when I plug it back in, it might be nice here, but it won't be here. We'll be left with a square root, right? So let's just solve for H. It'll be a little faster anyway. So H equals 50 over 3W squared. Now I go through the reason, I go through explaining which one to solve for because that can really make or break one of these problems. It could save you a ton of time. And remember how important we've talked about time is. Okay, so the better you get at recognizing which variable is easiest and fastest rather to solve for, then that's going to save you a lot of time. Okay, so come on down here now. We're going to substitute that in. So we still have 60W squared, but instead of 48WH, we're going to put 48W 50 over 3W squared. And we see some stuff happening right away. Let's see here. I noticed that 48 is divisible by 3 because 8 plus 4 is 12, and that's divisible by 3. So let's take care of that W first. 3 divided by 48 though, let's see, that's 18, 6, so 16. Yeah, 30 plus 18, so 10 plus 6. And this could be 16 times 50. Great. Blah, 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 blah. Let's finish simplifying this first. 60w squared plus, let's see, 50, and so 50 plus 30 is 80. That cannot be right. 800. It's be 800 w to the negative first. I just put w to the negative first because that's going to help us when taking the derivative. So let's take the derivative. And I noticed, do I have room here? I think I gave myself some more room. Yeah, we got room. Okay, good. Alright, so C prime is equal to 120w plus, actually minus or plus negative 800w to the negative second. Now, let's combine this and make this one big fraction because remember the next step, ooh, I don't have a whole lot of room. The next step we're going to be doing is finding the critical numbers, and it helps a lot to have that in fraction. And also might want to factor out, well, let's make it one big fraction first. So 120w, I have, this is 800 divided by w squared, right? So if you guys want, I could write it like that, right? That might help out. How did I get this next step? So I'm going to take this, I'm going to multiply this side by w squared over w squared. So you actually get w cubed over w squared, right, when you combine the fractions. And last thing I'm going to do, I did notice, I think it's 40 is divisible. 120 goes in, 40 goes into both of those. So let's do a 3w cubed still minus 50, I believe. Yeah. W squared. Cool. So critical numbers. Critical numbers we're going to have when w squared equals 0, and we're going to have when the numerator equals 0. So let's get that over here. So we have w squared equals 0. That's just going to be 0, right? And we have 3w cubed minus 50 equals 0. So 3w cubed equals 50. So w is going to be the cube root of 50 over 3. And I'm just going to plug this into the calculator real fast. And yeah, that's about 1.882. Again, you want to use the store feature in your calculator to save that all the way out to the point that you need the decimals. So what do we do now? Now we're going to do a number line, right? So let's draw our number line here. I'll do that down here actually, so we have room for our answer. And so we have two critical numbers we need to worry about. One is 0, and the other one is about 1.882. And remember, this is C prime. So I'm going to be plugging numbers in. I can plug them in right here. That won't be too much of a problem. If I plug in a negative number, this is going to be negative. The w squared is always going to be positive, so this will be negative. So I know that's going to be negative there. If I plug in 1, that's going to be 120 minus 800, also negative. If I plug in a really big number, though, eventually 120w is going to be larger than whatever this is, especially because the bigger the number you plug in, 800 divided by that big number is going to be a smaller number. So this is going to be positive. You can picture like, 10, okay? That's 1,200 minus 8, because 800 over 100. So, so we get a positive, and yeah, so what's the deal? Well, 0 is not a maximum or minimum because it's decreasing and decreasing, right? But here it's decreasing and then increasing, and we wanted a minimum, minimize the cost. That's good. This is our minimum, right? And what is it we need to find? We need to find the, we need to find the dimensions. Determine the dimensions. So we need length, length, width, and height, okay? So this was W, right? So the width is 1.882. To find the length, we just need to multiply the width times 3. So 3 times, let's actually do the cube root of 50 over 3, okay? And you plug that in, that actually is approximately 5.646. So there's our length, right? So we have width, we have length, we also need height. And we have, fortunately, this one right up here, 50 over 3 w squared. And so I believe, let me double check this. I plug it in and you get, is that true? A nice round number? Did I do something wrong? Let's see here. W equals, oh, I'll show you guys what I'm doing here. Sorry. There you go. Oh, I already have a W. Let's do this. Okay. we have 50 over 3. I prefer using, oops, I gotta put parentheses there, shoot, to the 1/3 power. Okay, rather than cube, it's just easier to type in or faster to type in. Oh, I must have typed in something wrong before. That's funny. Check and make sure. You know what? Aha! I have a typo here. This was from my notes. This should not be 50 because 800 divided by 40 is 20. Whoops. Okay. Kudos to those. I'll mark it in red here so you guys see. That should be 20. Sorry. 20, 20, and 20. The funny thing is, it still is 1.882 because I did this work earlier. So that's the 20 there. There we go, 20. Okay, that makes me feel a lot better. So here we go, 20. Glad we did that. Yeah, there's the 1.882. So let's just plug this in. We have 50 over, we're trying to find the height now, 3w squared, and we get, that's not what I had before, good, 4.705. So we have height is 4.705. So we want to answer this. We can answer with a sentence. The dimensions are 1.82, and we are measuring in feet by 5.646 feet by 4.705 feet. There we go. All right, just a few more here. That one I think is, in my opinion, one of the more difficult ones, just because of trying to find this cost equation. I think is the tricky thing, making sure you're counting all the sides. But once you realize, oh, how did I know that was surface area? Well, first of all, it's materials to build the box, so you're going around the edge. The other thing is, if you notice here, that over feet, square feet, that's the other thing you can use to say, oh, that's surface area, so we need to count all the sides. You just go around and count the sides. And notice how helpful having a picture there was for that part. Okay, here we go. A manufacturer needs to make a cylinder that can hold, cylinder can, that will hold 1.5 liters. So I'm going to draw a cylinder here. Let's do this. I did this earlier, and yeah, you can make straight vertical lines with that. That is so nice. I want the back dot of this. I'm gonna try to freehand it. That's not too shabby. And we'll keep it. Awesome. So here we go. So we know the volume is going to be 1.5 liters. Determine the dimensions that can of the can that will minimize the amount of material. So we're minimizing this time. And so the material, again, that's going to be surface area, right? So things I need to know, and of course these will be given to on the test and on the AP test, okay? But it's just helpful to know anytime you have volume, it's just base times height, right? So if I have this as the height, then volume is going to be the base, which in this case is a circle. You should know the formula for area of a circle times height. Okay, so volume is pi r squared height. But instead of volume, I know the value for that, so that's going to be 1.5. Notice one of the things we were careful about before in as we were doing the related rates problems. Remember we said don't plug in the numbers you know until you've taken the derivative. Well, we're not taking the derivative of this one, right? So we can plug in the number now. We're taking the derivative of the other one. So that's something that we're still sticking true to. We're just not taking the derivative of the one we're plugging into. So, but the material, the surface area, which is the thing we're taking the derivative of, involves the base, the bottom and the top, right? So that's going to be pi r squared is the base. And there's two of them, because there's two circles, one on the bottom and one on the top, so 2 pi r squared. Plus the area on the side, and the area on the side, just like you would guess, is just the circumference of the circle times the height. Because if you unroll it, you actually get a big, like, imagine cutting the paper off of a can. You unroll it, you get a giant rectangle, right? So it's just going to be the circumference, which circumference is diameter times diameter times pi, so 2 pi r. and then times the height. Okay, so 2 pi r h. So here's our surface area, and here's our volume formulas. Let's solve for one of these. Once again, I'm looking here, I'm going, all right, which is the easiest to solve for in this equation? H is going to be the easiest to solve for because I don't want to deal with a square root. So let's draw an arrow because this is not equal, but we have H equals 1.5 over pi r squared. Now we're going to substitute that in here for H. Again, it's also nice to choose the thing that reduces how much you have to substitute in, right? So I'm only substituting in for the H there rather than substitute for all the R's. So 1.5 over pi r squared. We see some nice things happen again. There's a common theme. So r divides out with r. The pi divides out with pi. And so we get 2 times 1.5 is 3. So our surface area before we take the derivative, 2 pi r squared plus 3 over r. This is going to be nice to take the derivative of. So let's take the derivative. I'm going to do the real hack here. I'm just going to do surface area prime, the derivative of the surface area, and that is a function, right? Equals 4 pi r plus, minus 3r to the negative second. You can think of this, remember, as 3 times r to the negative first to take the derivative of it. Let's combine these fractions, because this is, of course, a fraction. So we have 4 pi r minus 3 over r squared, right? So I'm going to multiply the top and the bottom by r squared over r squared. So we get 4 pi r cubed minus 3 all over r squared. The reason to do that is because now we want to set it equal to 0 so we can find the, we want to find the critical values. So we set it, we don't set it equal to 0, we set the numerator equal to 0, which is setting the function equal to 0. And we're going to set the denominator equal to 0. So that's equal to 0, and r squared equals 0. R squared is fast to solve, right? That'll be r. Here, let's add 3 to both sides and divide by 4 pi. So we get r cubed equals 3 over 4 pi. And take the cube root. There's no plus or minus because cube roots don't have a plus or minus. 3 over 4 pi. And so those are our two things. So let's punch that in the calculator. You get about, 0.620. Again, we want to store that in the calculator. And let's make our number line. I think we'll have room to do that up here now. So let's make our number line. Remember, this is for the surface area derivative function. And here we actually have two things, 0 and 0.620. If you plug in, and where are we plugging in? Into the derivative function, so we can use this right here as an example. You plug in a negative number, it's going to be negative and negative because that's r squared will be positive, but you have a minus there. So the whole thing's going to be negative, so we have a negative here. Plug in the number between 0 and 1. Well, one thing is actually right here, if you look at this, the multiplicity of 0 is going to be 2, so it's going to stay the same. You can also picture plugging in a very, very small number will make this number very large because when you divide by small numbers it gets really large, so that's going to be negative. Plug in a really big number, like say 100, this is going to be bigger than that, so we get a positive. So we get negative, negative, positive. Once again, 0 is a critical number, but it is not a extrema, relative extrema. So 0.620, we're decreasing, then we're increasing. And did we want a minimum? Yes, we said minimize, right? Awesome. But what do we need? We need the dimensions. And so we have one dimension, 0.620. This is the radius, right? We also need the height. And we want to look for our formula that solves for height. There it is. Oops, there it is. That's going to be the, okay, hello. Computer's lagging a little. Here it is, right? That's where we're going to want to plug in. So we plug that in there. And when you do that, so we're plugging in, actually remember the stored number, I got that height was 1.241, okay? Now you might be asking, okay, wait, what are the units in this? Especially because we started with liters, and that's volume, but liters is not anything cubed. It actually is, and this is something you're not going to have to memorize, okay? I'll share this with you on a test or whatever. It's actually cubic decimeters. So with our answer, we can answer it like this. Again, that's not something I would expect you to know, it's something that as a science teacher it's nice to know, right? So the dimensions are 0.620 decimeters for the radius and 1.241 decimeters for the height. You actually don't need any other variables because radius and height is all you need for a cylinder once you tell someone it's a cylinder. Great. All right, let's go on and do the last problem here. We have a piece of cardboard that is 14 inches by 10 inches, and we're going to cut out the corners as shown below. Unfortunately, I decided to remove the picture because I didn't like it, so here you go. You're going to have to fill this in, draw this picture shown below. And those of you guys who are fortunate enough to have me for pre-calculus, you might remember we actually did this in class where we spent a whole day just cutting out boxes. The cool thing is I had no idea that this was a common calculus problem. I'm really excited by the fact that it is. And it's slightly different than the one we tackled. Okay, pretend that's a square there. Sorry, bad drawing. But it same idea, right? So, whoa, let's try again. Swing and a miss. This needs to be vertical. There we go. And picture these are straight lines, right? The dotted line is where, I'm drawing the dotted line because that's where we're folding it, okay? And so when you cut out these corners, right? And the corners all have to be squares, otherwise when you fold it up, this side and this side don't line up, right? So they're all squares in those corners. And when you fold it up, you get like this section right here, that right there is going to be this base, okay? So you get this base here. And then when you fold up the sides, you get sides that are like this, right? And then fold up a side, that's a side you fold up. And then this is a side you fold up, and that's the last side you fold up, right? So it's a box with no lid. The top is open, so there's just a base to worry about. And so it wants us to determine the height of the box that will give a maximum volume. One thing you should notice is that this right here, when you fold it up, that and that, that's this right here. So that is the height of the box. So we can start labeling this. If I want to write H 100 times, you can, knock yourself out. You don't have to if you recognize it with the first few. But all of those are all the height, right? The other thing that it tells us is that this is 14 inches by 10 inches, okay? So when we go, inches, there we go. When we go and mark, like, say, okay, we have our volume of the box. What is that width? Well, that width is here to here. And notice that's just the 10 inches minus h, right? In other words, 10 minus 2h, okay? Likewise, I'll pick a little different color for the other one. Here, this is just this length right here, right? From there to there. And that's going to be 14 minus 2h, okay? Because you have the whole 14 top to bottom minus h and minus h. So we have 14 minus 2h, and we have 10 minus 2h, and we have h. So the volume of the box, make this in black actually, the volume is going to be h times 10 minus 2h times 14 minus 2h. And yeah, that's nice because guess what? We don't need two equations. We have the entire volume right there set up for us, right? Now, we are going to want to multiply it out, but then we can take the derivative and we can determine the height. So let's do some stuff here. Here we go. Let's multiply this out. I see 10 times 14. Don't forget to multiply this h, so we have 140h. Then we're going to have negative 2 times 14, that's negative 28. And negative 2 times 10, that's negative 20. So negative 20 and negative 28, negative 48. It would just be h, but we have the h out in front, so that's going to be h squared. And then negative 2 times negative 2 is positive 4, and the h's are going to multiply out. Would be h squared, but we have h here, so h cubed. And you can, let's see, what do we do here? You could factor out a 4, I noticed. There's a 4 in here and a 4 in here. So we could do that, right? Oh, you know what? Trying to see if I'm forgetting something. Oh, no, I'm not. Let's take the derivative before we factor anything out. Okay, so let's take the derivative. That's what I wanted to do. to write that in blue. I'm getting a little bit weird here. Okay, so let's take the derivative. So we get 140 minus 96h plus 12h squared, right? And we can rearrange this, put this one in the front if you want. Other thing you could do is I'm also going to factor out a 4 at this point. Let's see here, the 4, that's going to be 3h squared left over. I see 48 divided by 4 is 12, so double that, 24, because I had to double that for that. It's just a little arithmetic. 140 divided by 2 is 70, divided by 2 is 35. Divided by 4 is the same as divided by 2 twice. At this point, I'll go and share with you, you can try to factor it, I did for a little bit, but it's actually not factorable. So we can use the quadratic formula. So opposite b, and so what am I doing? Sorry, this is equal to 0, right? So we can divide both sides by 4 and just leave off at this, right? Because that 4 is not going to give us a 0. So we're trying to find the zeros of this. Let's use the quadratic formula for that, right? So opposite b plus or minus square root of b squared minus 4ac. The reason I didn't put negative 24 is because when you square it, it's going to be positive anyway. There we go. All divided by 2a. And here we're going to use a calculator, okay? So we plug that into calculator. You get 1.918 equals h, or 6.082 equals h. And both those come from the plus or minus, right? Now it really helps us if you've been sticking along and doing the number line each time. The number line will help us here. I'll show you some other things it'll show. But yeah, so we have 1.918 and 6.082. Let's check for positive or negative. So positive, negative, I'm looking back up here. Remember, this is v prime that we are graphing here. So whether it's positive or negative. If I'm looking here, if I plug in a really big number, that h squared is going to be way bigger than anything else, like plug in a million. A million squared is way bigger than a million. So if I plug in a really big number, it's going to be positive. And because this is a quadratic, each of these are going to have multiplicity 1, so they're all going to be odd. You could also try plugging in a number, like if you plug in 0, for example, 0 and 0, so it's just 35 times 4, or 140. So yeah, we're going to be positive there, and in between it is negative because of the negative 24 is the largest, is the most, is the value that's the value that's furthest away from 0, so that's why it's negative. Okay, so we have positive, negative, positive, so we're increasing and then decreasing and increasing again. Let's look for what we wanted. We wanted the maximum volume, right? So we're looking for what's the maximum volume. That's going to be right here, actually. And so what we get is that's the height. It says, the question said determine the height of the box that will give the maximum volume. So there's a maximum. So 1.918 inches is the maximum volume. Maybe I should say a height of 1.918 inches is the maximum volume. And I just real quick wanted to show you guys a graph of this. Did I lose it? I probably lost it. No, we'll just, okay, we got to type it in again. Here we go. So if I come here, I can actually even type in my original equation. I just want to show you guys. V equals, let's see if it accepts it. It does. Good. Minus 2h, 14 minus 2h. And again, if this graph will bring back some memories, if you were in my pre-calculus class, you'll see we have our cubic. Why is it cubic? Well, because it's volume, right? And so we have our maximum here. What's interesting, that's the 1.918, and it gives a maximum, the volume it gives is 120.164 cubic inches. What's interesting is that other number, that 6.082, actually gives a negative volume, which is not really possible. And so you can even consider, for some, 5 is actually the largest possible thing you cut. In fact, when you cut a 5, it makes a volume of 0. That's because coming here, if we were to cut 5, make these a height of 5, this box, the cuts would be here, and it would go like edge to edge, and so you wouldn't have any paper to fold. You just would have this silly little paper that you would just fold in half, and it'd be a tall box with no volume. So That's one thing we talked about is the constraint here. Because of 10 minus 2h, you need a number less than 5 in order to have a box at all, right? So the domain of this box would have been, this height could have been between 0 and 5, not really including 0 and 5 if you don't want a volume of 0. So, hope this helps, and thank you guys for watching.